Hi, in this tutorial we are going to practice drawing chair conformations of cyclohexanes. The question asks, draw the two chair conformations of cis 1-ethyl 2-methyl cyclohexane, then decide which conformer is more stable and explain why. In order to solve this question, we have to draw chair conformer of cyclohexane, and drawing chair cyclohexane is easy, but it requires a little bit practice. So let's summarize how can we draw in a couple of steps the chair cyclohexane. You need to draw a line, then you need to replicate this line. You need to draw a parallel line, but lines should be a little bit slanted, looking downward, and the second line has to be offset a little bit to left. Then this way we draw 4 carbon, that is making the plane of cyclohexane, chair cyclohexane, and the 2 carbons has to be connected to an upward carbon, and the other 2 carbons, they have to be connected to a downward carbon. Then this way we can draw chair cyclohexane. I prepared exactly 2 chair cyclohexane here. Then we can draw our 2 chairs for this given molecule. So how can we draw cis 1-ethyl 2-methyl cyclohexane? In order to do that, you need to number carbons on the chair cyclohexane. You can do arbitrarily, but I always start from the upper carbon as number 1, and the second is number 2, 3, 4, 5, 6. You can number this way. So let's start drawing. We need to draw an ethyl substituent, ethyl group on the first position. You can either start with an equatorial ethyl or axial ethyl, but let's start with axial one. Okay, we draw an axial ethyl here, and in the second carbon we have to place a methyl group, and depending on where we place axial or equatorial, we need to get a cis isomer, cis conformer. So let's look at it has to be cis. So if I place an axial methyl group, axial methyl and axial ethyl on the subsequent carbons, they are going to face in opposite direction, so it's going to be trans. So the methyl group in the second carbon has to be on equatorial position. So we decided this, and then this is our cis isomer. And on the second template we can draw another chair cyclohexane, which should correspond to again cis. So how can we do it? So we can change the axial ethyl to equatorial ethyl. Then at that time we have to change the equatorial methyl to the axial position, so that we can get the cis. So basically sometimes students might have some issues how to draw cis or trans. You can decide easily this way. When you have an axial position and the next carbon's axial position, if you place substituents on axial positions on the adjacent carbons, it's going to be always trans. But when you place one of them on the axial, one of them on the equatorial positions, it's going to be always cis. But this is only true for 1,2 disubstituted cyclohexanes. Okay, then after placing substituents on the first and second positions, let's decide which one is more stable. So we have to look at any strain present on the cyclohexane. Basically, we know that angle strain plus torsional strain, and the only strain might present in substituted cyclohexanes are 1-tridiaxial interactions or 1-tridiaxial strain, which is a type of steric strain. So in order to decide which one is more stable, we have to place, or we have to visualize the 1-tridiaxial strains. In order to do that also, we have to place all the axial hydrogens so that we can understand what type of 1-tridiaxial interactions we have for both conformer. I am placing all the axial hydrogens available for conformer A. Let's name it conformer A. So I placed 1, 2, 3, 4, 5 axial hydrogens because the sixth axial hydrogen is or that position is occupied by the ethyl substituent. For the conformer B, let's place all the axial hydrogens. And yes, this axial position is occupied by the methyl in in conformer B. Okay, now let's decide what kind of 1-tridiaxial interaction exists in A. So we have ethyl axial position which is interacting with 2 axial hydrogens. So basically ethyl hydrogen axial interactions, we have 2 here. In the second conformer, we have methyl and axial hydrogens interacting 1, 3 and 1, 3. So this is 1, 2, 3, and if we count from the opposite direction 1, 2, 3, this interaction is here. So we have 2 1-tridiaxial interaction which are between methyl group and hydrogens. Here in A, we have 2 diaxial interactions which are in between ethyl and hydrogens on the axial positions. Which one causes more strain? Basically, more bulkier groups. Bulkier group should have more strain. So ethyl should be ethyl is definitely bulkier than methyl, so the interaction in A is causing more strain. So we can say that A has more energy and A is less stable than B. Okay, so we decided which one is more stable, which one is less stable, which one has more energy, which one has less energy. Sometimes you need to also look at any gauche interaction might exist in cyclohexanes, 1-to disubstituted cyclohexanes. If you have equatorial, if you have axial equatorial, if you have equatorial and axial positions occupied by methyl, ethyl or other substituent, definitely there will be a gauche interaction. How can we visualize a gauche interaction? Basically, 3D models are better in this case. So we have here, we can show 2 models, and this is for A and this is for B. If you look at A, and if you look through carbon-carbon bond in A having methyl and ethyl substituent, the dihedral angle between methyl and ethyl group is 60 degrees. So this is a gauche interaction, which is a steric strain. And do we have the same interaction in B? Let's look through again carbon-carbon bond which carry methyl and ethyl substituent. Yes, the dihedral angle between methyl and ethyl is 60 degrees. So we have gauche interaction for 2-chair conformer, which means that when we are comparing stability of A with respect to stability of B, so gauche interaction do not cause any strain, because it causes strain, but when we are comparing, so they will have both same strain because of the gauge interaction. So the only parameter deciding which one is more stable, basically one tridiaxial strain. We can again visualize here. For A, we have an axial methyl group and two axial hydrogens, this hydrogen and ethyl group, and this hydrogen and ethyl group. So this causes more strain, more steric strain than the methyl axial and methyl hydrogen interactions in conformer B. Thank you so much for watching.